name is Chuan Qin from Hohai University. And the topic of my presentation is control strategies for a hybrid offshore renewable power generation system integrated into power grid. The contents of my presentation are as follows. The first, I will introduce a kind of hybrid offshore renewable power generation. The second, I will introduce the dynamic control of the hybrid system. It's optimal optimized parameter tuning method to improve the dynamic performance of the hybrid system. And finally, I will introduce the steady state control of the hybrid system with battery energy storage. This is the schematic diagram of the hybrid renewable generation system. The hybrid system contains wind turbine and wave energy and tidal energy conversion systems. The hybrid system is proposed to improve the utilization of the offshore renewable energy and to reduce the cost, because there are only one structure mounted three kinds of offshore renewable power generations. The wind turbine is mounted on the top of the structure, and the AWS-based direct drive wave energy conversion system is inside the jacket structure. Because the jacket structure is hollow, so it will not affect the wave power capture of the AWS. And here is the tidal turbine. Then is the next is the power conditioning, or the electric interface with the power grid. Diffig generator is used for wind turbine, and linear generator is used for AWS, and permanent magnet generator is used for tidal turbine. And the linear generator and the PMSG are connected to the DC link, via two converter. And there is also a converter to interface the DC link with the grid. And so there are five PWM controlled three-phase voltage source converter. So there also have 5 control blocks. This is the rotor side controller of the field, and this is the grid side controller. And also is the generator side controller of AWS and generator side controller of PMSG. Also have generator side controller of grid side controller of PMSG and AWS. It shows that the five controller block totally has 11 PI controller, 11 PI regular. So it has 22 control parameters. We know the control parameters greatly affect the dynamics, the dynamic performance, because incorrect parameter setting will worsen the dynamic performance, even result in the instability. So optimization-based parameter tuning method is used to coordinate the parameters of multi-controllers. However, as mentioned before, the control system of single hybrid unit has 22 parameters. So for a hybrid farm with many hybrid units, so a large number of parameters in the control systems. So it's difficult to optimize the parameters simultaneously. Then the problem is how to reduce the optimized complexity. In other words, how to reduce the numbers of the parameters in optimization. We use the sensitivity-based method to identify the key parameters. The key parameters play important roles on system dynamics. So I will introduce the concept of sensitivity. The sensitivity reflects the derivative relations between the system dynamics and the system parameters. So it can be calculated by this equation. And y is the trajectory variables, and k is the control parameters. Also, we can calculate the mean sensitivity by this equation. And the mean sensitivity can be used to identify the key parameters. If the mean sensitivity of a parameter is larger than the others, so it shows that it will play important roles on dynamic response. So the hybrid system is integrated into a 4-machine bus system. A 4-machine system. It's a 4-machine 2-area system. And a single phase ground fault on the middle of line 1 is applied to excite the dynamics of the system. And this is the mean values of the sensitivity. There are 3 lists, and the first is the sensitivity respect to the active power of the hybrid system. The second is the sensitivity reactive power of the hybrid system, and the third is the voltage bus. Is the sensitivity reactive voltage bus. So it can be found that the red one we can treat the red one as the key parameters because the sensitivity, the value is larger than the others. And in here, it should mention that it should be noticed that they only have 16 parameters, but the total control system have 22 parameters. So why they only have 16? Because the AWS and the Tidal turbine is buffered by the DC link. So the initial cannot be seen from the grid side. So if you calculate the sensitivity, you can find that the other 6 parameters sensitivity is very small. So they only have 16 parameters. So now we have totally 22 control parameters and 8 key parameters. So we use a PSO algorithm to optimize the 8 key parameters. The objective function is to minimum the overshoot. And the stop conditioning, they have 2 stop conditioning. The first is the time count is greater than the maximum number. And the second is there is no solution improvement of a specified number of generations. If one of the stopping conditions is satisfied, then stop. And this is the optimal. This is the results. The black line is the original is the original parameters. The red line is the results of optimized 16 parameters, and the blue line is the results of optimized eight parameters. So it can find that after the optimization, the dynamic performance is improved, and the dynamic response of the optimized 16, the red line and the blue line, they are similar. They are similar. The dynamic response is similar. So we can use the 8 key parameters to we can only optimize eight key parameters to improve the dynamic response. When I calculated the sensitivity, I found an interesting thing. I found something very interesting. But firstly, I will introduce a simple example. There is a simple second-order linear system with feedback controller. And the closed loop system can be written as this. And so the characteristic equation can be written as this one. So we can find that in this equation, the dynamic response of the closed loop system is determined by K1 plus K2. Not K1, not K2, but K1 plus K2. That means, in other words, if I optimize the parameters, if I optimize the K1 plus K2, maybe it will have a unique optimal solution. But if you optimize K1 or K2, it will have the optimal solution of K1 or K2 are not unique. So we name it that K1 and K2 are undistinguishable when they are optimized separately to improve the dynamic response. In other words, that in this equation we can find that K1 and K2 have relationship with each other, have K1 plus K2 this relationship with each other. But for a high order nonlinear system, such as the high-rate system collected into power grid, it's difficult to obtain the analytic relation between the parameters. So we can see this picture. We can find that the red one is the sensitivity curve, is the sensitivity curve of KP3, and the blue one has the sensitivity of KP2. And we can find that these two sensitivity reach 0 at the same time. This is the sensitivity respect to reactive power. This is the sensitivity related to active power. Both the sensitivity are reached at the same time. So we have some mathematical proof, but maybe not strict, that if the sensitivities reach 0 at the same time, the corresponding parameters coupled with each other or have relations with each other, just like this K1 plus K2. But the relationship is difficult to get. So the parameters are undistinguishable, and the optimal solution are not unique. We have some numerical verification. We calculate the optimal solutions with different objective functions. This is the overshot, and this is the setting time, and this is the IAE. You can find that all the three optimal solutions are not unique. You can find this in this area, and in this area. The KP2 and KP3 have many solutions that the overshoot is keep constant and in the minimum values. So, but it should be pointed out that we only find the relationship between the sensitivity and the distinguishability, but it is not used to the optimization of the control parameters, and I think it will need further study. Thirdly, I will introduce the steady state control of the hybrid system. We know the output power of the hybrid system varies because due to the immigrant nature of the energy source, of the renewable energy source, and the battery energy storage is used to smooth the power fluctuations. And the condition, the coordinate control we proposed between the hybrid system and the battery energy storage has the capability of handling SOC constants. The SOC constants we define as from 20% to 90%, and in this control method we have three control models. Normal is first is the normal model, and the preventing of overcharge model and the preventing undercharge model. Maybe you will find that the normal model and the preventing overcharge model and the undercharge model, the SOC limit is larger than the SOC constants. It's because we should restrict the SOC in this area, so the control will be implemented earlier. So it's the control strategy. There have two trigger, overcharge trigger and undercharge trigger, and the trigger the output of trigger is enable and unable. It will switch to switch the control to switch between the control models. And the battery energy storage is connected to the DC link via a DC to DC converter. And the control objective of the battery control is to maintain the DC voltage control, maintain the DC voltage. So in the normal model, the generator side controller is maximum power point. The objective, the control objective of generator side controller is maximum power point. The control objective of battery controller is maintain the DC link voltage as its nominal value. It's by the control block is like this. And the grid side controller is power smoothing control. There is a P reference, is a reference of the grid side power. The P reference can be calculated via numerical low pass filter. And this is the similar results. We can find with the when with battery, the output power is smooth. And the second is the preventing overcharge model. The control objective of grid-side controller is also the power smoothing control, and BES control is also the same as before. But when the battery will be overcharged, it means that we should reduce the output power of the generator side converter. So the overspeed and the pitch control is used to reduce the generator side converter power, and it's the characteristic curve about the rotor speed and the power. You can find the omega optimal respond to maximum power, and if you increase if we increase the rotor speed, the power will be reduced. Will be reduced. So the power reduced, the overcharge will be maybe it will not overcharge for the battery. But it should be mentioned that there is omega max. If you use overspeed control, the maximum deload power delta P only in this point can be seen in this point. And the priority of wind and tidal generation side controller depend on the wind speed and the tidal speed. Actually, it depends on the capability of the deload of the generator side deloading. And for the overspeed and the pitch control, the overspeed control have higher priority because the dynamic response of the speed control, its electrical controller, is faster than pitch control. Pitch control is a mechanical controller. And secondly, the frequent pitch control may lead to wear and tear. And it's the flow chart. We can see the simulation results. Without overcharge control, the output power fluctuations. With overcharge control, the output power is also smooth. And with overcharge control, the SOC decrease. Without overcharge control, the SOC is higher. Finally, is the preventing undercharge control when SOC is smaller than 25%. In this control model, the grid side controller is the objective function of the objective of the grid side controller is to reduce the power reference. Then use such a feedback control. The SOC and SOC minima are put into the input of the error of SOC and the SOC minima are the input of the PI controller. Then plus the P generator PG reference. Then we can get new reference of reference power of the grid side. And it's the simulation results. You can find with undercharge control, the SOC is increase. Okay, that's my presentation. Thank you.
This production is brought to you by the University of Edinburgh.